Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from the Electrical Engineering at IIT Hyderabad. We will begin our second module today, where we will discuss the trends in global memory market and memory array architecture and the peripherals. This will put us in a good position to start discussing individual elements from the memory hierarchy. So, a brief recap of what we have been covering till now. We saw that memory hierarchy is arranged in a pyramidal fashion because it indicates that as you go down in the hierarchy, the bit density or the capacity improves, it increases, but it comes at the cost of latency. And there are different memory device technologies which are employed at different levels in the hierarchy to fulfill their own needs. For example, in the L1, L2 and L3 caches, you have your SRAM cells made up from the same transistor technology as the logic elements as well. Your main memory consists of your 1T, 1C DRAM cells. This forms the infrastructure for a tightly coupled memory subsystem. Going from DRAM to NAND flash, you enter primary storage, where the objective is for preserving data, and this is done using the flash cell, which consists just of a single transistor. Emerging non-volatile memories, which are still being developed, are these two terminal devices, which can act as both memory elements and storage elements. That means you will have fast access times with high bit densities. So as you see, as you go down in the memory hierarchy, the size or the footprint of an individual device or the cell is reducing, but the cost you have to pay is higher latencies. So today we will begin with a review of memory hierarchy. Why are we emphasizing so much in the memory hierarchy? This is because before we go into individual cells and individually memory elements, you should be very confident what are the requirements of that particular memory or storage element. So we will review the concepts of memory hierarchy from a different perspective today. As you can see in front of you, you have a relatively complicated image indicating the computing needs or the computing infrastructure or the hardware for computing from a more memory-centric perspective. That is why on the top left corner, you see you have abstracted the CPU subsystem with its multiple cores. So you have core 1 to core n. Remember why we had multiple cores? This was to have some semblance of parallelism in the von Neumann architecture, which is inherently sequential. The other way of including parallelism, if you remember our discussion, was to have pipelining. And that is why your L1 caches, which is indicated here in orange and purple color, have two kinds of, there is a subdivision in the functionality of the L1 cache between data caches and instruction caches. So as you know from the as you can understand from the name, the instruction caches store the next important immediate instructions, which is to be run on the respective core. That is why there are separate L1 data and instruction caches for each core. Coming back to the next level of caches, which is L2 caches, you can see the L2 caches here indicated in green color and interface through the CPU subsystem interconnect also is specific to individual core. So as many number of cores, generally same number of L2 caches allotted to each core. The interesting thing in L2 caches is, here the necessity for pipelining is not that important. So there is no distinction between L2 instruction and data caches. L2 caches can hold both instruction and data. Followed by a large common resource of cache, which is your L3 cache. The L3 cache in some systems can be implemented using eDRAM or embedded DRAM technology, but in most cases still they are implemented using SRAM cells. So this is the whole CPU subsystem in its full glory, along with the logic elements of core and L1, L2 and L3 caches. This CPU subsystem, as you may know, talks to the main memory, which consists of DRAM cells. And as you can see in the image, this is how the DRAM cells look when you buy them from the market and you slot them inside into your motherboard. So this is just a interesting representation of that. And this DRAM talks to the CPU subsystem through an important element called the memory controller. So this part, if not memory controller, in this section or in this module, we will also look at what are the important elements of memory peripherals. The next element which I am indicating to you now consists of your primary storage. The primary storage, which is also called flash, indicates that you may have a little delays in accessing data, but the focus is on preservation, followed by more archival form of data preservation, which are called RAIDs. So RAIDs, expanded, are redundant array of inexpensive disks used primarily in servers to store data which is very, very, very infrequently used. As we indicated, the essence of memory hierarchy is the competing effects between latency and size. Let us look at them with specific numbers on this particular occasion. We will not discuss much about the CPU registers because they are intrinsic part of running of this course. We will start with the L1 data and instruction caches. As you can see, the speed of the L1 and L2 caches is very large. They are in the order of 1 to 10 nanoseconds. Considering that nowadays these CPU subsystems run at the frequency or clock frequency of about 3 to 4 or 5 gigahertz, you can estimate that to retrieve data from L1, L2 caches, it takes roughly 10 to 100 clock cycles, which is indicated here in green. Now, there is a big difference in the size of L1, L2 and L3 caches, where L1 caches, both instruction and data, in the order of few KBs, because they are most expensive to fabricate. So you need to limit the amount of the footprint. So they have only around 16 KB of L1, L2 caches, of L1 caches, both instruction and data. So together it is around 32 KB in the order of tens of KBs, whereas L2 caches, the size is in the order of hundreds of KBs. Now remember that L2 and L1 caches are specific to individual cores. And therefore the L3 cache, which is a large bank or a repository for very frequently used data and to be shared amongst all the caches, is quite large, and that is in the order of few MBs. Next, we look at main memory, where you guys are very familiar about. Generally, whenever we buy mobile phones or computers, what is the size of the main memory that you are generally obsessed with? It is in the order of 4 to 64 GBs, with very high end workstations even having 128 GBs. So as you know, you can have the memory hierarchy pyramid in front of you. As you see, as you are going down in the hierarchy, the size is, or the capacity is, gradually increasing. Next, think about what are the kind of NAND flashes or the flash technology or the storage memory that is currently available in the market. It is starting from 512 GB. Yes, earlier generation used to have pen drives, but now I think pen drives are becoming obsolete, and you are having, in a very small footprint, data capacity of anything from 512 GB to 1 to 2 to even 10 TB. We will not discuss about redundant RAIDs because they are not very important for immediate computing needs, only for very specific niche server technology. Again, try to recall your entire CPU subsystem consisting of L1, L2 and L3 caches was part of your on-chip technology. This is the most generic representation. This lecture itself, we will see how a modern day mobile phone application processor completely breaks this paradigm. But this is still what is generally the case. The on-chip memory is restricted to the cores and the L1, L2 and L3 caches. And you have two separate off-chip memories and storage. The first off-chip memory is your DRAM, and your second off-chip memory is your NAND flash. Please recall why they are off-chip, because they are essentially being fabricated in separate foundries and integrated on the motherboard through external wires. The second important thing to recognize is the distinction between memory, which is generally volatile, has to be very fast, and closely coupled to the CPU subsystem or the cores. As you know, DRAM is where this boundary between DRAM and NAND flash, or the main memory and the main storage, is where this boundary is being drawn. Storage elements, which consist of NAND flashes and magnetic tapes, are essentially non-volatile, but they are very slow. The advantage is you will have very high bit density and therefore very large volumes in the orders of terabytes, petabytes. The second thing we will look at is the device technology. We have already seen this several times, so let me run through this a little bit quickly. Your registers consist of your latches and flip-flops. Your SRAMs, as you can see, the footprint has gone down quite drastically from roughly 20 transistors. An SRAM cell, using similar concepts of positive feedback loop, which we will cover in detail very soon, is consisting only of 6 transistors. Your DRAM consists of just 1 transistor and 1 capacitor, and your NAND flash consists of just single transistor, and of course you have your magnetic disks. What is essentially essential to recognize over here is the size of the memory element is reducing as you go away from the CPU subsystem, and therefore you will have very high bit densities and capacities, but you are suffering in speed. Also, we discussed that while this is the traditional implementation of your computing infrastructure from a memory perspective, as you can see over here also, there is a several orders of magnitude gap in the latency, whether you see in speed or in clock cycles. Between 100 clock cycles of time that it requires to recover data from main memory, that becomes almost 10 to the power of 6, 4 orders of magnitude difference when you want to recover data from the or access data from the primary storage. This huge gaping hole, the promise is that electronic non-volatile memories will address. Okay. So with this, let us move forward and look at two practical examples of how the memory hierarchy is being implemented in consumer electronics, not just normal consumer electronics, in two specific example of high-end consumer electronics. So we look at the implementation, the actual implementation of memory hierarchy and the concepts what we have been studying in the phones and laptops that you are using. So the first example is that of an high-end a mobile phone, which is Samsung Galaxy S20. So there are several companies who do these so-called tear downs. What is the meaning of tear down? Tear downs can happen at several levels. Here you see that a company called Tech Insights or a website called Tech Insights has done a detailed analysis or a tear down of the motherboard PCB of the Samsung Galaxy S20. And as you can see, there are a lot of chips in the motherboard. Is because it is a phone, it will have primarily the chips related to the application processor and the modem. Because it's a phone, you need to have a modem to connect to the network, and there is a 5G modem also. But that is not our what we want to discuss. What we want to discuss is the implementation of the memory hierarchy. So, for your benefit, I have marked out two of the chips. The first chip, which I am now indicating with my laser pointer, is the following. It is a 12 GB LPDDR5 DRAM, which is co-packaged with the processor. What is this chip? It consists of your CPU or your logic element and co-packaged with DRAM. The size of the DRAM, if you notice carefully, is 12 GB of DRAM, which is quite decent for a high-end phone. Other important element which I have marked out for you is the main storage, which consists of a 256 GB NAND flash. So, in this kind of arrangement in the motherboard, do you notice something which is deviant? Some concept which is deviant from what we have been discussing till now. Please take a moment to pause, to think about this and see that there is something off or something different from what we have been discussing. And if you have been following the course very carefully, you will know that generally, since we discussed the DRAM consists of one transistor, one capacitor technology, they are fabricated in different foundries, it is generally out of chip memory. It is not on chip memory. However, your Samsung Galaxy S20 breaks this paradigm by co-packaging your main memory, which is your DRAM, with the processor. And how is it done? This is done through this very interesting concept of heterogeneous integration. When we look closely in DDR or DRAM technology, later on in our course, we will cover what heterogeneous integration is. Heterogeneous integration essentially is the technology of integrating two chips made from completely different foundries into the same die. How do you co-package them into the same die? And because of advances in heterogeneous integration, you are able to include DRAM into the same die as your as your CPU. And what is the advantage that you get? That is in latency, in performance. It is clear to know, it is very easy to understand that if the DRAM was separated from the CPU subsystem and put as a separate die, the wires that were connecting the DRAM chip or the main memory chip to the CPU subsystem would cause a lot of latency, right? So the essence of showing these example to you is to make you aware that memory hierarchy is entirely fluid and it is continuously evolving according to needs of computing. Okay. Next, let's look at the second important subsystem or product that some of you, including me, are using. It is the tear down of your MacBook Pro. So let us look at this really interesting motherboard. The source of getting this image is from the website iFixit. So they also do a good job at finding out what the latest consumer electronics implementation on the motherboard looks like. So since there are a lot of chips in the motherboard of MacBook Pro, let me draw your attention to the ones of specifically our interest. So the first thing is marked in red outline. As you can see, it has the Apple logo, and this essentially consists of your M2 processor. As you know, earlier Apple was using Intel's processors. Now they have come up with their own processor. The first generation was M1. Now we have the M2 processor. It is a 64-bit octa-core processor. What does that octa-core mean? Please remember what we were seeing in the previous slide. In order to have parallelism, you were integrating many cores into the CPU subsystem. So this particular chip has 8 cores. So you can do parallel processing with 8 cores. What very interesting to see also is that this 8 core also has a GPU or a graphics processing unit. Why is this graphics processing unit become very important in modern day chips? It is because graphics processing units essentially accelerate matrix multiplications, specifically vector matrix multiplications. Why is this vector matrix multiplications very important? For data-driven computing like AI/ML computing, the fundamental operation is vector matrix multiplications. And that is something we will see in detail in the second half of our course. Okay, now that we understand what is there in the logic processor or the logic chip, let's see what is tightly coupled or right next to the logic chip. It is your 2 chips indicated in orange color, and these are 2 chips of LPDDR5 4 GB each DRAM memory, and this is coming from a company called SK Hynix. SK Hynix, as we will see, is a large giant South Korean memory design company or memory manufacturer, and they have a large market share in producing DRAM chips. As you can see, the DRAM chips are very tightly coupled to the processor. Just a little distance away is a chip which is indicated with yellow boundary. What is this chip? This is again a chip coming from SK Hynix, but it is a 256 GB NAND flash memory. 256 GB NAND flash memory. This is a good indicator of what the memory hierarchy looks like. Not just in your pyramidal diagrams, even in an actual motherboard, you can see that your DRAM is much more closely packed to your to your CPU subsystem compared to your NAND flash. What is the size of the NAND flash? It is 256 GB. Here, please pause, take a moment and think that there is a very important observation you can make based on whatever we have studied till now. If you have been following the course very clearly, you will see that it looks like the footprint or the area consumed by just two chips of 4 GB each consisting of main memory DRAM is comparable or even a little bit more in area compared to the 256 GB NAND flash. Why is this happening? Please recall, when we were comparing the NAND flash and the DRAM, we saw that the bit density of NAND flash is generally 8 times. That of NAND flash is 8 times that of DRAM. And this is what is also indicative roughly in the motherboard. Of course, we are ignoring the area occupied by peripherals and we will come to that very soon. But roughly, as you can see, 8 GB of DRAM is consuming almost the same space or maybe a little more compared to 256 GB of NAND flash. The next thing that I would draw your attention to is those blocks with these bluish boundaries. So here is one of the blocks, here is another of the blocks. So you have 3 such blocks. Let us focus on the block which is on the left hand side of the screen. These consist of 8 MB serial NOR flash memory from a company called Macronix. Let me repeat, it is 8 MB of serial NOR flash memory. Compare this in footprint to the 256 GB NAND flash memory. 8 MB versus 256 GB. Orders of magnitude larger bit density in NAND flash compared to NOR flash. Please recall, the fundamental cell in NAND flash and NOR flash is essentially the same. It is your floating gate transistor or your charge trapping transistor. So what explains this large difference in the area? And the answer to this is very simple, and we will see it in detail when we study about NAND flash and NOR flash technology. Whereas NAND flash technology is serial, NOR flash technology is random access. We have been discussing that of course you would want random access for larger, faster access times, lower latencies, but it comes at the added cost of peripherals and the area of which is occupied with these more involved peripherals. This is what is very indicative. Important thing to understand is, why would you want a NOR flash in this kind of cells? Because there can be some permanent data. Remember, DRAM cannot store data permanently in the sense that it is essentially volatile. So there might be some application such as running the boot code right when your chip is booting up. You might want some information which is permanent, but you want to access it as soon as possible. So the latency for permanent data in certain applications you would want to have very, very small. And this is where NOR flash can play a very important role. So generally you store the boot code in NOR flash so that you can have non-volatility and fast access times because of random access capability. The final thing that I want to indicate to you is this small chip which is indicated with pink color. This is essentially your EEPROM. What is EEPROM? It is electrically erasable, programmable, read-only memory. Yes, we have read-only memories and specific technologies which ST Microelectronics really has mastered in read only memories, but we will not really go into the device aspects because the volume of these read only memories and importance in the memory hierarchy is very, very limited. But since we have come to it, let us discuss why you need read only memories. So, as the name suggests, read only memories are those kind of memories from which you can only retrieve data. You cannot write data. So, essentially, the application space is some security codes or some essential features of the chip that you want to hard code. This is where you use read only memories. And what is electronically erasable programmable? It consists of a technology using UV light to read and to permanently store information into the read only memory. Okay, so with this practical examples of memory hierarchy, let us close today's session. In the following session, we will discuss about how these chips are being manufactured and what is the global memory market, what is the net worth in billions of dollars of these chips, focusing on memory and storage chips in the contribution in the global economy. Thank you. Let us meet in the next session.